Sam hears the refrigerator stop at 9:17. The battery display still shows charge. The panels worked all day, but one loose connection warmed, voltage sagged, and the inverter protected itself by shutting the cabin down. Here's the whole path: panel, controller, battery, inverter, protected load. 5 handoffs. One weak handoff can stop the plug even when every expensive box is present. This is the lesson most shopping lists skip. Solar power does not jump from a panel into a wall outlet. It changes form, crosses limits, waits in storage, and passes through protection before a lamp can turn on. We will trace that trip without hiding behind abbreviations. Then we will commission the system in a deliberate order and diagnose 3 common failures from evidence, not guesswork. We will use one household from beginning to end. The V37 teaching cabin is exactly V36's 2-adult, 640 square foot Flagstaff cabin with a 7.20 kilowatt-hour daily planning load, non-electric space heat, water heat, and cooking, a 3.2 kilowatt sensible array, and an 18 kilowatt-hour nominal 2-day battery. V35's 7.19 kilowatt-hour result belongs to a different 720 square foot load reduction worksheet, so the 0.01 kilowatt-hour difference is example boundary and rounding, not a changed claim. That sentence is the household boundary. We are not shrinking its loads or sizing its panels again. We are following the energy that the V36 system was meant to deliver. Keep one question open while we work. If the panels are producing and the battery has charge, where can the power still disappear before it reaches the plug? Start with a map, not a brand. Sunlight reaches the panels. The panels produce direct current electricity. Direct current means the electrical push keeps one direction. That power moves through protected solar wiring to a charge controller. The controller changes the panel's varying voltage and current into a charging pattern the battery can accept. The battery stores energy as direct current. When the cabin asks for ordinary household power, the inverter draws from the battery and creates alternating current. Alternating current reverses direction many times each second. That is what most familiar cabin outlets and appliances expect. After the inverter, power moves through an alternating current disconnect or distribution panel, then through branch protection and cabin wiring to the final load: the refrigerator, pump, light, laptop, or tool. Panel to controller, controller to battery, battery to inverter, inverter to distribution, distribution to load. Those are the 5 handoffs. Protection sits beside the path, not outside it. Fuses, breakers, disconnects, grounding, bonding, enclosures, cable supports, and strain relief are not bonus accessories. They limit damage, make isolation possible, and give a technician a safe place to test. Their exact selection belongs to the equipment manuals, adopted code, local authority, and a qualified designer or electrician. The Department of Energy calls the non-panel equipment the balance of system. The name is dry. The consequence is not. A panel can be perfect while an underspecified controller clips production. A battery management system refuses charge in cold conditions, an inverter trips on a pump start, or a loose terminal adds resistance and heat. The map gives us a diagnostic rule: test in path order. Do not start at the most expensive box. Find the last handoff that is behaving normally. The fault usually sits at that handoff or immediately after it. The panel does not send a fixed amount of power all day. Its voltage and current move with sunlight, temperature, shade, wiring, and the connected equipment. The label on the back gives operating and limit values under stated test conditions. It does not promise the same output on a cold dawn, a hot roof, or a cloudy afternoon. The charge controller has an input window. 2 limits matter before energy can move safely: how much solar voltage may arrive and how much charging current the controller can deliver. Cold modules can produce higher open circuit voltage than their warm rating suggests. That is why final string design must use the exact module datasheet, the controller manual, the lowest expected temperature, and a qualified calculation. We are not calculating a string here. We are learning what the handoff must prove. First, the solar disconnect is in the intended position. Second, polarity is correct. Third, conductors and connectors belong to the system and are seated correctly. Fourth, measured array voltage is inside the controller's allowed input window. Fifth, the controller recognizes the battery side before it is asked to process solar power. That last point surprises beginners. Many controller manuals require the battery connection first so the controller can identify the system voltage and establish control before the panel side is energized. Follow the exact manual for the actual unit. Do not copy a sequence from a different controller. What does failure look like at this first handoff? The controller may show 0 solar voltage. That suggests an open disconnect, an open fuse, a disconnected conductor, a connector problem, or no usable light. It may show solar voltage but almost no charging current. That can be normal when the battery is full or loads are small. It can also point to shade, a current limit, a thermal limit, or a battery side refusal. The measurement is more useful than the emotion. Record time, weather, panel side voltage, charging current, controller state, battery voltage, and any error code. One clean snapshot gives the next test a starting point. The controller's job is not simply to push everything it receives into the battery. Its job is to charge within a defined profile and stop or reduce current when a limit says so. Battery chemistry, temperature, state of charge, voltage, current, and battery management rules all matter. A lithium battery can appear to have energy while its internal protection has opened the charge path, the discharge path, or both. A cold charge limit can reject solar input even though the display remains alive. A high current event can cause a protective shutdown even though the battery is not empty. That is why percentage alone is weak evidence. State of charge displays depend on configuration and calibration. At this handoff, voltage, current direction, temperature, alarm history, and the battery manual tell the fuller story. Our canonical cabin carries V36's 18 kilowatt-hour nominal storage position for the 2-day teaching case. That number is not permission to parallel any batteries that fit the arithmetic. Each battery family has rules for maximum continuous current, charge current, temperature, wiring symmetry, series or parallel arrangement, communication, terminal torque, and external protection. Think of the battery as a guarded reservoir. The controller can offer energy. The battery decides whether the offer is acceptable. If the conditions are outside its rules, the gate closes. The protection near a battery deserves special respect because a battery can deliver very high fault current. A conductor that merely looks thick tells you almost nothing. Length, material, insulation rating, temperature, routing, termination, continuous current, surge current, fault current, and the protective device all matter. This is where internet shopping list advice becomes dangerous. For the lesson, keep the commissioning proof simple. With solar isolated and cabin loads controlled, confirm the battery bank matches the documented system voltage, polarity is correct, terminations pass the specified inspection and torque procedure, required protection is present, battery temperature is allowed, and the controller reads a plausible battery voltage without an alarm. If that proof fails, stop. Do not energize the solar side to see whether it fixes itself. The inverter makes household-style power, but it cannot create energy or ignore current limits. On the battery side, the inverter asks for direct current power. On the cabin side, it provides alternating current voltage and frequency. Between those sides are conversion losses, idle consumption, temperature limits, continuous output limits, short surge limits, and protective shutdowns. The useful distinction is continuous power versus starting power. A refrigerator compressor or well pump may need a short burst above its running demand. The inverter has to carry that burst. The battery and conductors also have to deliver the required direct current surge without voltage falling below the inverter's limit. This is not a repeat of the V35 load lesson. We are not changing the appliances. We are locating the constraint in the path. Suppose the well pump starts. The inverter display reports low battery voltage and shuts down. The battery percentage looked adequate before the start. That does not prove the inverter is defective. The battery voltage may be sagging under load because of low charge, cold conditions, a weak battery, excessive cable resistance, a loose termination, or a battery management current limit. Measure before and during the event using the procedure and instruments approved for the system. Compare the voltage seen at the battery with the voltage reported or measured at the inverter input. A large difference under load points toward the path between them. A similar collapse at both ends points back toward the battery state or battery limits. The inverter also protects the alternating current side. Overload, short circuit, excessive temperature, abnormal output, and ground fault-related conditions may cause a trip or shutdown depending on the unit and installation. Read the actual error. Do not reset it repeatedly until the reason disappears from history. An error code is a witness. Photograph it. Record the load that was starting. Record battery voltage and temperature. Then isolate the system using the approved procedure before touching any connection. Once the inverter is running, the system can still fail after it. Alternating current power should pass through the intended disconnect and distribution equipment, then branch protection, then fixed wiring, then the outlet or hardwired load. A powered inverter with a dead receptacle can mean an open output breaker, a tripped branch breaker, a protective device that is operated, a failed transfer arrangement, a loose connection, or damaged cabin wiring. The correct response is not to bypass the device that opened. A breaker is not an inconvenience to hold closed. It is evidence that the circuit exceeded a condition it was selected to handle, or that the device or circuit needs inspection. Before anyone resets it, write down which device opened, what was running at that moment, and whether anything nearby smelled hot or looked discolored. If the same device opens again after one allowed reset, the circuit is telling you the same thing twice. A third reset is not troubleshooting. It is erasing the evidence. At this part of the map, the line between owner observation and qualified electrical work must stay clear. An owner can note which circuits are affected, which indicators are present, what load was operating when the event occurred, and whether a reset allowed by the manual holds. Opening live equipment, measuring exposed conductors, changing protection, or altering fixed wiring belongs to a qualified person working under local rules. Now answer the opening question. If the panels are producing and the battery has charge, power can still disappear at the controller's limits, the battery's protection, the battery to inverter path, the inverter's protective logic, the alternating current distribution, or the final branch circuit. The panel is only the first witness. The plug is the last witness. Everything between them needs a known normal state. Commissioning means proving the system in a controlled order and saving what normal looks like. It is not the ceremonial moment when every switch is thrown on. Before energizing, the documentation should identify equipment models, serial numbers, manuals, settings, conductor routes, protective devices, disconnects, labels, and the one-line diagram. Photograph the finished installation before covers hide the path. Record the approved torque checks and inspection results. Confirm clearances, ventilation, weather protection, cable support, enclosure condition, and required warnings. Then follow the manufacturer's and qualified designer's startup sequence. The exact sequence controls. A general teaching sequence is cabin loads controlled, solar input isolated, battery side verified, controller powered from the battery if its manual requires that, controller settings confirmed for the battery, inverter input verified, inverter started without a major load, output checked, branch circuits introduced deliberately, and solar input connected according to the controller manual. At each step, pause and record. Battery voltage at rest. Controller battery reading. Controller solar voltage and charge current under known weather. Inverter input voltage. Inverter output voltage and frequency. Idle power. A small known load. A larger ordinary load. The well pump start if the qualified commissioning plan includes it. Temperatures and alarms. NREL operation and maintenance guidance treats commissioning data as a baseline. That baseline makes later troubleshooting faster. If today's controller current is half the normal value under similar conditions, you have a comparison. If battery to inverter voltage drop is larger than at commissioning, you have a direction. If an enclosure is warmer than its baseline, you have a reason to stop and inspect. The same cabin should be commissioned in 3 operating configurations. These are not 3 system sizes. They are 3 states of the one declared power path. Configuration 1 is the sunny charging state. Ordinary cabin loads are modest. Solar input is available. The controller is charging. The battery current may be positive while the inverter also serves a load. Record array voltage, controller output current, battery voltage, inverter input, alternating current output, and the weather. This proves that energy can cross every active handoff while the sun is carrying part of the cabin. Configuration 2 is the night discharge state. Solar input is absent. The battery is the only source. Start with a small known load, then use the qualified commissioning plan for one ordinary larger load. record battery voltage, direct current draw, inverter output, and any voltage drop across the battery to inverter path. This proves that the stored energy can leave the battery and arrive at the cabin without borrowing evidence from the solar side. Configuration 3 is the controlled isolation state. The approved shutdown procedure separates the system at named disconnects so a qualified person can confirm which sections are de-energized and which sections may remain dangerous. The panel side can remain energized in light. The battery remains an energy source even when the inverter is off. An alternating current circuit can have another source if the design includes a generator or shore input. The isolation receipt must therefore name the boundary instead of saying, "the power is off." These three states expose different faults. A controller problem can hide at night because the controller is not needed. A weak battery-to-inverter connection can hide at noon because solar charging holds voltage up. A mistaken isolation assumption can hide until service begins. Proving all three states closes those gaps before an emergency does it for you. This cabin needs 4 receipts on screen. Receipt 1, the one-line path with every disconnect and protection point named. Receipt 2, the component limit table. Not marketing power. Maximum input voltage, charge current, battery current, continuous inverter output, surge duration, and temperature windows from exact manuals. Receipt 3, the commissioning baseline with date, weather, battery state, voltages, currents, loads, temperatures, and alarms. Receipt 4, the shutdown and isolation order posted where a qualified person can use it. The receipts turn memory into evidence. Failure 1. Sunny day. Controller shows no solar input. Start at the panel to controller handoff. Confirm whether the weather can support production. Read the controller state and error history. Check the approved external indicators and disconnect positions. A qualified person then follows the documented isolation and test procedure for panel side voltage, protection, wiring, and connectors. Do not jump to replacing the controller because it is the first screen you can see. Failure 2. Controller shows charging, but the battery state keeps falling. Compare energy entering with loads leaving over the same period. Check whether the battery is accepting charge or limiting it. Record battery temperature, voltage, current direction, alarms, and controller charge stage. Confirm that inverter idle consumption and ordinary cabin loads are included. The fault may be insufficient harvest, an unrecorded load, a battery side limit, a measurement configuration problem, or a degraded connection. The trace stays at the controller to battery handoff until the evidence is normal. Failure 3, battery shows charge, but a pump start kills the cabin. Read the inverter shutdown reason. Record battery and inverter input voltage before and during the start using the approved test plan. Compare the 2 readings. Inspect logged current and temperature limits. A collapse across the cable path suggests resistance or protection in that path. A collapse at the battery points towards state, temperature, capacity, or battery management limits. A stable direct current supply with an inverter overload points toward the inverter/load relationship. The method is the same every time. Name the symptom. Freeze random changes. Save alarms. Draw the 5 handoffs. Find the last normal measurement. Test the next handoff safely. Change one thing. Test again. Update the baseline. Here is the Field School 5 for this lesson. Replacement. This power path replaces grid delivery for the declared V36 cabin loads. Load, 7.20 kilowatt hours per day is carried forward, not recalculated. Cost, protection, disconnects, conductors, documentation, and commissioning are system parts, not leftovers. Catch, every component has a limit, and the limit can stop power while the box still looks alive. Starting point. Draw panel to controller to battery to inverter to protected load, then write the normal measurement at every arrow. Sam's cabin did not go dark because sunlight vanished. The loose handoff added resistance. The pump start pulled harder. Voltage fell at the inverter. The inverter shut down before the connection became a fire. The shutdown was not the failure. It was the warning that worked. The next decision is not a bigger panel or a smaller load. It is whether the cabin has enough storage to carry the declared service through the night and the weather. That belongs to the next lesson.